Hello and welcome to week 9 of NPTEL live session on the course of Foundations of Cryptography. So let me share my screen. So first I will just go through the last week assignments that were posted on NPTEL website. So first question was select the incorrect options. If P is prime, then ZP star is a cyclic group of order P. So as you know that if P is prime, then ZP star actually excludes the identity element. So ZP star actually excludes the zero element, right? So if you consider the multiplication modulo group, so ZP star is actually excluding the element 0, and rest of the elements are part of the group ZP star. ZP star denotes all the elements in the set ZP which are co-prime to the number P, to the prime P. So basically all the integers which are less than P except the element 0 will be co-prime to P because P is a prime number, right? So all the elements 1 to P minus 1 are co-prime to P. So that's why the order of the group, that is number of elements in the cyclic group, that will be P minus 1. So order is not P, rather it is P minus 1. Proceeding to the second statement, that is the point at infinity O acts as the identity element of the group E plus, where E is the set of points on a non-singular elliptic curve. So as you know that there is nothing to explain, it is just by default assumption for any elliptic curve under the binary operation, like point addition on elliptic curve. There we consider this point at infinity to be the identity element. So this point is assumed to be lying on all the y-axis. So for all the y values where somewhere at the infinity, all these vertical lines through various x values, they meet. So you consider that point to be the point at infinity. Third statement is the negative of a point on an elliptic curve is its reflection in the y-axis. This is wrong. Basically, negative of a point is taken to be the reflection of that point with respect to x-axis. We have already seen that, right? So say in point x comma y on the elliptic curve, we take x comma minus y to be its negation inverse, the point with respect to point addition operation, because x comma y plus x comma minus y gives us the identity element point at infinity. The fourth statement, in a prime order group, every element of the group is a generator. This is again wrong because in a prime order group, every element except the identity element is a generator. So in a prime order group, there are say q minus 1 number of generator if order of the group is q. So the identity element is not a generator. So our correct options were the second statement and the only second statement, right? That was the only correct option. All other options are incorrect. Next question. So which of the following points satisfy the curve y square equal to x cube plus 22x plus 25 mod 47? There are 4 options given. Actually, there is nothing to explain in this question. You just put the value of x and y. Say, for example, for the first option, 25, 28, you replace the value x with 25 and you replace the value y with 28 in the given curve and check whether the both left hand side and right hand side in modulo 47 space gives the same result or not. If you check with that method for all the 4 options, you will finally get them as answer. First and second point will be found to be lying on the elliptic curve. Third question. Choose the correct options with respect to public key setting. The ciphertext may not be always correctly decrypted to its corresponding plain text. This is true because there is certain cases where your your encryption algorithm is usually a randomized algorithm, and even if it is not, say like key generation algorithm is randomized algorithm, so there may be, with respect to some particular crypto system, there may be some specific key which are not actually valid key and does not ensure correctness of the form that decryption with respect to key of some encryptions of some message M with the same key K will gives us back the same plain text M. This correctness property does not hold with respect to some particular key value K. Maybe with some negligible probability, but it may happen. Also, it may happen that your encryption was correct. So your encryption algorithm being some randomized algorithm, but due to some error value, due to some improper value of randomness that was included during encryption process, the decryption may not result into correct plain text value. Okay, so there may be such cases, although with negligible probability. So the first statement that ciphertext may not be always correctly decrypted to corresponding plain text, this is true. However, any valid encryption scheme should try to make this probability negligible. Right. Second statement, an adversary does not have access to encryption oracle in a COA setting, that is ciphertext only attack setting. So with respect to, as we are talking about public key setting, so as you know, in public key setting, always the public key PK is available to the adversary, or it is available in public. Anyone can see the public key PK. So does the adversary. So having access to the public key PK, the adversary can get actually encryption of any plain text that it may want to see the ciphertext for. So it may pick any plain text M of its choice, and it just compute itself the value of encryption of M with respect to the public key PK. This is not the case for symmetric key encryption scheme, because in symmetric key encryption scheme, there is only one key K which is used to encrypt and decrypt both. But in case of public key encryption, you have two keys, one public key PK and another secret key SK. So the public key PK is available to everyone. And for encryption, you need the public key PK only. And for decryption, you need the secret key SK. So only legitimate user who has the secret key SK corresponding to some particular public key PK, he or she only is able to decrypt the ciphertext and get the corresponding underlying plain text. But the encryption is some public operation. So encryption algorithm, decryption algorithm, all these algorithms are public, if you remember. So we don't keep the algorithm secret in any encryption scheme, right? So algorithms are public, but the key, secret key is not public. But encryption key, PK being public, anyone has access to some encryption oracle, you can say, because it is able to get the encrypted value or get the ciphertext corresponding to any plain text of its choice. We don't need to explicitly give some encryption oracle access to the adversary, as we did in the case of symmetric key setting, right? In symmetric key setting, in COA setting, ciphertext only attack setting, we just give the ciphertext to the adversary, but we don't give encryption oracle access to the adversary. When proceeding to CPA security setting, then we give the adversary the encryption oracle setting in case of symmetric key cryptography. But in case of public key cryptography, whenever we are talking about COA security, that only implies CPA security because the adversary already have implicit encryption oracle access. Now, third statement, single message CPA secure also implies multi-message CPA secure only if encryption algorithm is randomized. So, as you know, for CPA security, we need anyway that encryption algorithm has to be randomized. Deterministic encryption algorithm will not ensure CPA security in any way. But yes, if it is the case that encryption algorithm is randomized, then single message CPA security implies multi-message CPA security as well. So what is the difference between single message and multi-message CPA security? Just to recall, it is very similar to the symmetric key setting as well. So basically, the adversary chooses message, so individual message to different message M0 and M1 in case of single message CPA security, and it gets to see the encryption of any one of them. Right. And in case of multi-message CPA security, basically the adversary provides vectors of messages, say capital M0, which is consisting of some L number of messages, say small m 0,1, small m 0,2 to small m 0,L. So L number of messages are there in the vector capital M with subscript 0. And there is also capital M with subscript 1, capital M1, which is again consisting of L number of vectors, say small m 1,1, small m 1,2 to small m 1,L in this form, right? So there are two vectors, each of length L, and also we have this condition like we had in single message CPA security. We used to say that the length of message M0 should be equal to length of message M1. Here, in the vector, so in ith position of the vector, say M0I, size of M0I should be equal to size of M1I. That is also required. So you pass two vectors of messages, capital M0 and capital 1 in case of multi-message CPA security, and you get to see the encryption of any one of those vectors of messages. So either you see all L number of ciphertext corresponding to the plaintext present in capital M0, or you get to see the L number of ciphertext all corresponding to the L number of plaintext present in capital M1, right? And you have to distinguish whether you are seeing ciphertext corresponding to the plaintext present in capital M0 or plaintext present in capital M1. That is the case of multi-message CPA security. So anyway, now if the encryption algorithm is actually randomized, then it is single message CPA secure as well as multi-message CPA secure. And then fourth statement says perfect secrecy is easy to achieve. So as we are talking about public key setting, their perfect secrecy is not actually achievable in contrast to private key setting. In private key setting, you have already seen the construction of one-time pad, which is a perfectly secure symmetric key encryption scheme, but it is not possible in case of public key setting. The reason being that there is always two keys, right? PK and SK, right? Public key PK and secret key SK in case of public key setting, and there they have certain relation between them, right? Now, whenever you adversary has the knowledge of PK, it can basically search over the key space of secret key, like brute force attack or exhaustive search over the key space of secret key, and try to find out what is the valid secret key with respect to the available public key PK. So there is always an exponential time attack available to search for that, to search that adversary can search that what is the valid secret key with respect to the available public key that it can already see. So perfect secrecy cannot be achieved in case of public key setting. So the correct options here turn out to be the first option and then the third option. Right. Proceeding to the next question. Which of the following statements is or are correct? D-log is easy to solve for some additive cyclic groups. Well, this is true because anyway, in case of like additive cyclic groups of the form say ZP with respect to addition modulo P, you know that already this kind of group does not satisfy any of D-log, CDH or DTH assumption. And the second statement says D-log is easy to solve for some multiplicative cyclic groups. So in case of multiplicative cyclic groups as well, if you choose small parameters for the prime P, so there it can be the case that D-log is even easy to solve. So usually you choose like a prime order subgroup of some ZP star, right? Where the order will be again the order of the subgroup will be order Q, where Q is prime, right? In that case also, if you choose smaller value of parameters P and Q, then it is vulnerable to attack. So yes, first two options are correct, that in certain cases D-log is easy to solve for both additive cyclic group and multiplicative cyclic group. The third statement says CDH assumption is stronger than DDH assumption. This is wrong. Rather, you know that DDH assumption is stronger because with respect to the problem, CDH problem is a harder problem than DDH problem, because if you are able to solve CDH problem, if you remember, so what is the CDH problem? CDH problem, if you have a cyclic group G with capital G, cyclic group capital G with a generator small g, and you have the value of g to the power alpha and g to the power beta available to you, where alpha and beta are some value from the group ZQ. Okay, so what is Q? Q is the order of the group G, right? Or size of the group G. So basically any member of group capital G can be expressed in the form of small g to the power x, where x lies between 0 to q minus 1, and so that is it. Now when an adversary is provided with value g to the power alpha and g to the power beta, where alpha beta belongs to the set 0 to q minus 1, then with these two group elements available, the adversary should not be come up with the correct value of g to the power alpha beta, right? That is what is the CDH problem is. But if it is difficult for the adversary to come up with the correct value of g to the power alpha beta, then we say that the CDH assumption is true. And in case of DDH assumption, what we say is that you have been provided with triplet of the form g to the power alpha, comma g to the power beta, comma g to the power comma the third element. So you have first two element as g to the power alpha and g to the power beta, and third element could be of the form either g to the power gamma for some random gamma chosen from 0 to q minus 1, or the third element can be of the form g to the power alpha beta. Now the adversary has to distinguish between these two cases, that is the DDH problem. Now, if you are able to solve CDH problem, that is, you are able to correctly compute the value of g to the power alpha beta, seeing the value of g to the power alpha and g to the power beta individually, then you can easily solve the DDH problem as well, because indistinguishability is not anymore a problem. You directly compute the value g to the power alpha and check the third component value is equal to that or not, and you can correctly, like with probability 1, you are able to distinguish between these two triplets, Diffie-Hellman triplet or some triplet with the third component being any random element of the group G. Now, so basically what I mean to say is that the CDH problem is harder to solve than DDH problem, and hence we say that DDH assumption is even stronger assumption. If we are building some crypto system relying on the fact that DDH assumption holds true in that setting, then we are actually building the crypto system upon some stronger assumption, right? Fourth option, efficiently solving the DH problem implies efficiently solving D-log problem, that is discrete log problem. What discrete log problem says is that if you were given the value of some g to the power alpha with some unknown alpha, then you cannot easily come up with the correct value of alpha, right? Uh, okay. Now, efficiently solving DTH problem implies efficiently solving the D-log problem is not correct. Rather, D-log problem is a harder problem than DTH problem. So, you cannot say that solving DTH implies solving D-log. Rather, the reverse statement will be correct, that solving D-log problem will imply solving DTH problem. Okay. Because if you are able to solve D-log problem, what it means is that if you were given the element g to the power alpha, you were able to come up with the value alpha. And then, of course, what DDH problem needs is that to solve that you have g to the power alpha and g to the power beta, and the third component you have to see whether it is equal to the value g to the power alpha beta or not, right? And if you were able to determine the value of alpha from given g to the power alpha and value of beta from given g to the power beta, then you yourself can compute the value of alpha beta and then exponentiation, that is g to the power alpha beta. This computation is easy, and then you are easily able to say that whether the third component is equal to g to the power alpha beta or not. So that's why solving D-log problem implies solving DTH problem, but not the reverse statement. Okay, so fourth option is incorrect. And fifth option, that is efficiently solving CDH problem implies solving DTH problem. This is correct, as I already discussed, right? CDH problem is harder than DTH problem. So among these 5 statements, the first 2 options are correct, and then fifth option is also correct. Okay. So let me proceed to the next question. Let G be a prime order cyclic loop of order Q with a generator G. Then a commitment scheme is defined as follows. Alpha is the value the sender wants to commit to the receiver. To do so, it picks a random R from ZQ and sends the commitment R, G to the power alpha R to the receiver. To open the committed value, sender reveals alpha and receiver does the verification accordingly. Which of the following statements is or are true for this commitment scheme? First is, the scheme does not satisfy binding even if D-log assumption is true for G. The scheme does not satisfy hiding even if D-log assumption is true for G. The scheme does not satisfy binding even if DDH assumption is true for G. The scheme does not satisfy hiding even if DDH assumption is true for G. So basically, you have to comment upon whether this given scheme satisfy binding and hiding property of a commitment scheme. So if you remember, what the hiding property of commitment scheme says is that you have an you have a challenger and an adversary in the commitment scheme hiding game. Then the adversary actually outputs some message alpha beta of its choice, and in response the challenger chooses either alpha or beta to commit. So the adversary should not be able to know by seeing the commitment whether it is seeing a commitment corresponding to alpha or corresponding to beta. That is the hiding property says. So the adversary should not be able to distinguish between the commitment of alpha and commitment of beta except with negligible probability. And the binding property says that you have the adversary has already received the commitment. So here actually adversary is the sender. So when you are talking about binding property, you assume the sender to be corrupted and receiver to be honest. In contrast to the case of hiding property, where you assume the sender to be honest and receiver to be corrupted. So coming to the scenario of binding property, here the corrupt sender, which we can call adversary. So adversary first commits some value C corresponding to some message alpha, right? Now that is the commitment phase, which is over. Now in the revealing phase, the adversary actually reveals some other value alpha dash, which is different from actual alpha that was committed in the commitment C. So it reveals some other alpha dash to the receiver, and receiver, when verifies whether the commitment C is indeed a commitment of alpha dash or not, it gets that alpha commitment C is indeed a valid commitment of message alpha dash. So here basically receiver is being cheated, although C was initially a commitment corresponding to message alpha. During revealing phase or opening phase, the receiver gets to know that C is a valid commitment of alpha dash. So this cannot be the scenario. What we need is that if we are committing a value alpha with commitment C, then you cannot change the inside message alpha by any means except with negligible probability. So a corrupt sender should not be able to come up with such two different message alpha and alpha dash such that both of them are committed to same value C. Okay, that is the case of binding property of commitment scheme. Now coming back to our particular question, here you have been given with some construction of commitment scheme where alpha is the value the sender wants to commit to receiver, and for doing so it has picked some random r from ZQ and then sends the commitment r comma j to the power alpha r. So our claim is that the scheme neither satisfy hiding neither satisfy the binding property. And why is that so? So basically all four of these statements are correct. Okay. How is that so? Here hiding is not satisfied because we are actually revealing the value r also as part of the commitment value, right? So both r and j to the power alpha r, both these values are getting provided as the commitment value to the receiver. Now a corrupt receiver can now easily check it has the knowledge of alpha and beta because those were chosen by adversary itself. So alpha and beta are known to adversary. Also it can see the value r as part of the commitment. Now computing the value g to the power alpha r, both alpha and r are known to adversary. So g to the power alpha r can be easily computed in polynomial time, that is just the modular exponentiation. And g to the power beta r can also be similarly computed by the adversary, and it can then easily check. So it is saying the commitment r comma g to the power alpha r of this form, right? So this it can be either of the form r comma g to the power alpha r, or it can be of the form r comma g to the power beta r. And as both g to the power alpha r and g to the power beta r can be computed by the adversary, it can easily check that the second component of the commitment matches with g to the power alpha r or matches with g to the power beta r. And thus it can conclude that whether it is seeing a commitment corresponding to message alpha or corresponding to message beta. So hiding property is not satisfied, right? with probability 1, in fact, it can distinguish between commitment of alpha and commitment of beta. Now, what about binding property? Binding property is also not satisfied here, because here a corrupted sender basically may choose the R value to be 0. Okay. So in case it chooses the value R to be 0, then what happens is that g to the power alpha R, this value, so R is 0, alpha R is also 0, right? And g to the power alpha R is nothing but g to the power 0, which gives us the identity element of the group. Now, corresponding to any message alpha, whatever value is assigned, so whatever value is of alpha, with irrespective of that, 0 comma I is actually a valid commitment. So the sender basically during the opening phase, okay, once it has committed the value 0 comma I to the receiver, then in the opening phase the sender can send any alpha of its choice basically to the receiver, and receiver gets pulled here, because receiver tries to verify whether the commitment 0 comma I is a valid commitment of the value revealed by the sender or not, and it always gets whatever alpha value the sender reveals to the receiver during opening phase, the receiver always finds it to be a valid commitment. Hence we say that binding is failed here. So binding property is not satisfied. Thus we conclude that for the given scheme, neither hiding nor the binding property is satisfied. Okay, so these were all questions from last week. Now entering this week's topics, which includes LGML public key encryption scheme, then RSA assumption, RSA public key crypto system, hybrid public key crypto system, and CCA secure public key crypto system. So problem 1. Let PK, which constitutes of G, Q, small g and small h, is the public key, and Sk equal to x, which is logarithm of h with respect to the base g, be the secret key for LGML encryption scheme. So this is well-known format of public key and secret key of any LGML encryption scheme, right? The secret is x, and g to the power x, which is h, is revealed as public key. And the description of the group G, its size Q, and the generated small g is available in public. Now let a PPT adversary obtain a ciphertext C, which is equal to C1, C2 of some unknown plaintext M, encrypted as per the LGML encryption scheme using the above public key. The adversary picks a uniform random R dash from ZQ, where size of G is Q, and computes C dash equal to C1 dot G to the power R dash, comma C2 dot M dash dot H to the power R dash. Now there are few options given, that what is the underlying message of this modified ciphertext C dash. Okay. So adversary is seeing some valid ciphertext C, and it is modifying the ciphertext to change the underlying message of it. Okay. Integrity is broken clearly, but anyway, so let us examine. So what is the content of C1 and C2 basically? According to the LGML encryption scheme, see here that y will be some uniformly randomly chosen value by the encryptor or sender of the message. So sender chooses some value y from the space ZQ and computes g to the power y and provides the value g to the power y as C1, first component of the ciphertext. This is according to LGML standard encryption scheme. And what is the value of second component of ciphertext? That is C2. That is computed as the underlying plaintext M into this is nothing but the group operation, right? That I have represented as this dot operation. This is the group operation, binary operator of the group. So m dot h to the power y. H was already available publicly, which is nothing but g to the power x. So x is secret, but h is available publicly. So we basically compute h to the power y dot m. And h to the power y, as you know, is nothing but g to the power xy, right? And g to the power xy is, as you know, Diffie-Hellman key, which is indistinguishable from uniformly random element of the group. So anyway, this is the form that C1 and C2 have of some valid Elgamal ciphertext. Now what adversary does is that adversary computes C dash of the form C1 dot g to the power r dash. What does that mean? C1 is g to the power y dot g to the power r dash. This is nothing but g to the power y plus r dash, right? And the second component is C2 dot m dash dot h to the power r dash. And C2 has this form m dot h to the power y. So as a result, what happens is that m dot m dash and hy dot h to the power y dot h to the power r dash. That is nothing but h to the power y plus r dash. So in total, you can see here, you have the first component of the form g to the power y plus r dash, and second component of the form, say m double dash dot h to the power y plus r dash, where m double dash you can think of m dot m dash. Okay, so g to the power some value of the set zq, and then some message into h to the power that same value. Okay, this is a valued Elgamal ciphertext form for the message m dot m dash, right? So we say that C dash on decryption outputs m dot m dash. So after receiving this ciphertext C dash, what the receiver does this, that it has the secret key x with it, right? So it will compute first the value C1 to the power x. That will give it g to the power y plus r dash plus x, and then it will basically, what it will do is that this h to the power y plus r dash is also nothing but g to the power x plus y plus r dash, right? So it will compute the inverse of the element g to the power x plus y plus r dash, and will perform dot operation with that inverse element. That will lead to cancellation of this term and leaves us with m dot m dash, the underlying plain text. That is how Elgamal decryption works, right? So our answer is C dash on decryption will output m dot m dash. Okay. So here comes the next question. Suppose in RSA crypto system, we have an E which has at least 1 0 in its binary representation. Now let E dash be another RSA public key obtained by flipping one of the 0 bit in the binary representation of E to 1. Then what happens? So there are some statement about relation between E and E dash, whether they are co-prime or not, etc. Now see that if you remember in RSA crypto system, what is E? Is you can see it is the public exponent, right? So in RSA crypto system, you basically choose two large prime P and Q, compute their multiplied value n equal to P into Q, and you also compute the value of phi n, which is the number of elements present in the set Zn star, or in other words, the number of elements in the set Zn which are co-prime to the number n, right? So phi n is computed, that is the Euler-Taussig function. So phi n is computed as p minus 1 into q minus 1. Okay. Now you choose some E which is greater than 1, of course, and you compute D as E inverse modulo phi n, such that ED is congruent to 1 modulo phi n. So that is how actually then you output in comma E as public key and in comma D as the private key. So that is how RDC crypto system works. Anyway, here we don't even need to think of that. So what you need is that you are given a public exponent E which has at least 1 0 in its binary representation. That is okay. And if you flip any 0 to 1 of the binary representation of E, then what you get is that you get basically the value E plus 2 to the power I, depending on the which ith bit position you are flipping the bit, right? That is easy to understand, right? Now, our argument is that you know that E is co-prime to phi n, right? That is how you choose E. Otherwise, computing inverse of E modulo phi n would be impossible. So you need to choose E in RSA crypto system in a way that E is co-prime to phi n. And what is the value of phi n? That is P minus 1 into Q minus 1. And both P and Q are prime. And except 2, all other prime numbers are odd, right? So P and Q must be odd numbers. So P minus 1 will be even and Q minus 1 will be even. So as a whole, P minus 1 into Q minus 1 is even number. So phi n is even number. And because E is co-prime to phi n, E cannot be even. Because if E is even, then of course 2 is at least some common factor of E and phi n. But because phi n is even, E has to be odd at least, right? So E is odd. Now E is odd and E prime, as I said, that can be represented as E plus 2 to the power I. Whatever is the binary representation of E, you flip some ith bit position whose value was initially 0 and you flip it to 1. So what is the increased value of E? That is, you increase the value of E by 2 to the power I, right? So E dash is equal to E plus 2 to the power I. And now it is just easy to see that because E is odd, it does not have any 2 in its factorization, right? Even if E is some composite number, all its prime factors must be odd. So the prime factorization of E having no 2 or any power of 2 in it, E plus 2 to the power will also have like you cannot extract some common factor from E and E plus 2 to the power I, right? So that's how you can just observe yourself and you can conclude that E and E dash, which is E plus 2 to the power I, are co-prime to each other. So our correct option is that E and E dash are co-prime. Okay. So proceeding to the next problem. Suppose the Ilgamel encryption scheme parameter generation algorithms outputs safe prime P, Q and the public key G, H, where G is the generator of a prime order subgroup G of ZP star, where the order of G is Q. Okay. So the statements given are for CPA security, the plaintext space has to be necessarily G. This is true actually. So for Ilgamel encryption scheme, as we already we discussed as limitation of Diffie-Hellman key protocol also, that the output key is actually a group element, not some uniform random element of that space, right? Of the binary space 0, 1 to the power something. So it is some particular uniformly random group element. So same applies for Ilgamel encryption scheme as well, that whatever operation you do there, it is all according it is all around the group operations. Okay, so plaintext space also has to be necessarily in G. Okay. If you take any outside element than the group G, then your security is hampered. Okay. So obviously the second statement, that is for CPA security, the plaintext space does not matter. It is wrong, because just we said that plaintext space has to be necessarily G. Third statement says the scheme will not be COA secure if the plaintext space is ZP star. So this is also true, because as I said that if you just take, so let's say that you how you construct the group G, that is G is some prime order subgroup of ZP star, right? So you can choose some message M0. Okay, you have to vary the plaintext space, right? So you choose some M0 which actually belongs to G, and you choose some M1 which does not belong to G, but M1 belongs to ZP star. So because G is subgroup of ZP star, of course, any element which belongs to G belongs to ZP star, but not the vice versa. So you take two plaintext, M0 belonging to G and M1 belonging to ZP star, but not belonging to G. Having two such different plaintext messages, okay. Now, how you basically encrypt them in LCaml encryption scheme? You do some, you actually choose, say, some beta and compute C1 equal to G to the power beta, that is the first component of the ciphertext. And the second component C2 will be of the form H to the power beta into MB, right? Where B can be 0 or 1. Now, H to the power beta is, of course, some group element. So H to the power beta will belong to G. Okay. But M, depending on whether M0 belongs to G or not, the value of C2 may or may not belong to the group G. Okay. So exploiting this fact, actually, you can just distinguish between encryption of M0 and M1. Okay. So in like individually, the group ZP star satisfies closure property, and the group G, which is subgroup of ZP star, that will also satisfy the closure property. But if you are taking some element from G and some element which is not in G but in ZP star, so that after operating between them with the corresponding group operator, you get the result which must belong to ZP star, but you cannot guarantee whether that result will belong to G or not. Okay. So you can exploit this property to distinguish with non-negligible probability whether you are seeing an encryption of M0 or encryption of M1 by looking at the second component of the ciphertext. Okay. So the scheme will not be COA secured if the plaintext space is ZP star. You need it to be G. Okay. So that's why. So the first option is correct and the third option is correct. Okay. Next problem. Consider the following modification to the Diffie-Hellman key exchange protocol executed over a cyclic group of order Q with generator G. The sender and the receiver sends Ks equal to G to the power X and Kr equal to G to the power Y to each other, where X and Y are randomly selected from ZQ and outputs Ks dot Kr as the final key. Assume D log, CDH and DTH and all other related assumptions are true in the underlying group, and this modified protocol is executed in the presence of a semi-honest adversary. Then you have been provided with some options. Now just observe that Ks is given as g to the power x, which is available as the transcript to the adversary. So it is visible on the public channel, the value Ks, and the value Kr is also visible on the visible to the adversary, which is communicated to the public channel. And if the final key is of the form Ks dot Kr, this is nothing but g to the power x dot g to the power y, and which is g to the power x plus y, basically, right? But what CDH assumption says is that with the knowledge of g to the power x and g to the power y, it is hard to compute g to the power xy if CDH assumption holds true in that particular setting. But it does not say anything about g to the power x plus y, right? So even if CDH assumption holds true, even DDH assumption holds true, even after that, basically, the adversary. So from the viewpoint of the adversary, the output key is uniformly random and unknown. This is, of course, wrong. The adversary will completely know the underlying output key. This is true. Why? Because Ks and Kr both are available to the adversary, and Ks into Kr is nothing but applying the group operation once between them. So that can be done in public. So the final key can easily be known to the adversary by doing Ks into Kr. So, and from the viewpoint of adversary, the output key will be pseudo-random. So this is also meaningless. So the only correct option is that the adversary will completely know the underlying output key. Okay. Next problem. We want to construct a collision-resistant hash function over a cyclic group based on the hardness of D-log and related problems. For this, consider a prime-order cyclic group G of order Q with a generator G. Then consider the function f zqn to G, where f of alpha 1 to alpha n is equal to g to the power alpha 1, alpha 2 to alpha n. Here, each of these alpha I belongs to ZQ. Okay. So there is comment about whether F is collision resistant or not. Now it is very trivial to see that you can actually come up with two different sequence of values alpha 1, alpha 2 to alpha n, and some beta 1, beta 2 to beta n, such that their multiplication, if we are considering that this is a multiplicative group, then the value of alpha 1 into alpha 2 to alpha n, if it is equal to the value beta 1, beta 2 to beta n, which is of course possible to come up with such two in length different sequence of elements, which leads to same multiplication result, then it is basically giving back the same result due to the power that multiplication value, right? So it is very clear to see that this is not collision resistant. You can easily come up with such two different sequence of n number of group elements whose multiplication is same, multiplication value is same. Then the function f is not collision resistant. That is our conclusion. Okay. Now, next problem. Consider the following variant of Ilgamal encryption scheme. Let P equal to 2Q plus 1. Let G be the group of squares modulo P. So G is a subgroup of ZP star of order Q. And small g is a generator of group capital G. Private key is G, Q, small g, x, and the public key is G, Q, small g, h, where h is equal to g to the power x, and x belongs to ZQ. X is chosen uniformly. To encrypt a message M belonging to ZQ, choose a uniform R belonging to ZQ and compute C1 equal to G to the power R mod P and C2 equal to H to the power R plus M mod P. And let the ciphertext be C1, C2. Is this scheme CPA secure or not? So as you know, in the standard L-Gamal encryption scheme, we return ciphertext of the form C1, C2, but C1 has the form G to the power R and C2 has the form H to the power R into M, right? So basically H to the power R gives the value of G to the power XR, which is the key indistinguishable from any uniform random element of the group G, and then with that key we mask the message M. So we perform M.K. Okay, so that is what is the standard L-Gamal encryption scheme does, but here we are doing C2 equal to H to the power R plus M mod P. Okay, so just notice that addition is not the group operation here. So if we perform H to the power R plus M mod P, it is not guaranteed that the output C2 will belong to G or not. Okay. Any element inside G, any two elements which are inside G, if operated with the group binary operator, then due to the closure property, the output also belongs to the group, right? But because although M and H are belonging to G, the group G, their addition output may not be belonging to group G. Okay. But what is ensured is that whatever message M you have encrypted in the component C2, let's say like in a CPA security game, what happens? The adversary chooses its own M0 and M1, right? Now the challenger will encrypt either M0 or M1. So let's denote it as MB. Now C2 is of the form H to the power R plus MB mod P. Now C2 minus MB mod P is nothing but H to the power R, which is definitely a group element, right? So we will exploit this fact actually to check whether C2, like whether the value C2 minus MB mod P lies in group G or not by checking for both B equal to 0 and P equal to 1. Then we are trying to distinguish between the encryption of M0 from encryption of M1. Okay. Now, let's see the detailed explanation. So, let's see the challenge ciphertext is C1, C2, which is encryption of MP, whether B can be either 0 or M. Addition not being the group operator, C2 is not necessarily an element of G. May or may not be, right? Like I said just now. However, C2 minus MB mod P is necessarily an element of G because H to the power R, this value of course is an element of G. So the adversary basically now checks, after seeing the challenge ciphertext, it checks both for M0 and M1 if C2 minus MB mod P belongs to G or not. If the condition is satisfied for any one of M0 or M1, what I mean is that when you check C2 minus, so either it can be the case that C2 minus M0 mod P belongs to G and C2 minus M1 mod P does not belong to G. This can be one case, and another case can be C2 minus M0 mod P does not belong to G, but C2 minus M1 mod P belongs to G. For these two cases, you can definitely say that for the first case, M0 is the one which is encrypted, and for the second case, M1 is the message which is encrypted because it satisfies C2 minus MB mod P belongs to G. And you, in that case, you can say that MB is the underlying message which is encrypted. And you are ensuring C2 minus M1 minus B. Basically, if MB is M0, then M1 minus B is M1. And if MB is M1, then M1 minus B is M0. Okay, notation wise I am saying. So, if you are ensured by computing that C2 minus MB belongs to G and C2 minus M1 minus B does not belong to G, in that case, you can definitely say that C1, C2 is an encryption of MB. Okay, but there can be the case where both C1 minus MB mod P and C2 minus M1 minus B mod P belongs to G, both of them. Okay, then what will you do? Then actually, this can happen that let's say your underlying message is MB. So for that C2 minus MB mod P belongs to G, that is always satisfied. But the fact that C2 minus M1 minus B mod P is also belongs to G, that will happen with the probability half. Why? Because see that you took the subgroup G of ZP star with prime order Q such that P was equal to 2Q plus 1. Okay. Like you took P equal to 2Q plus 1. What is meant by that is that all your element, so half of your element present in ZP star will be present in G, present in the subgroup G, and half of them will not. Okay. Then the probability that any random element of the form C2 minus M1 minus B mod P belongs to G, that happens with probability half. Okay. So, and if that happens, then adversary outputs random bit B dash, which can be either 0 or 1. So it outputs you randomly 0 or 1 as the distinguishing bit when both MB and M1 minus B satisfies this situation that both belongs to G. Okay. So if we compute the probability that what is the success probability of the adversary that it is able to correctly say what is the bit B, whether it is seeing the encryption of M0 or encryption of M1. So that success probability we compute. So success probability of adversary, probability of B dash equal to B. B dash is the bit that adversary returns. Okay. So that is nothing but probability of C2 minus M1 minus B mod P belongs to G. Okay. So this is one event into half. Half means that if this happens that M1 minus B satisfies this condition, then as I said, the adversary randomly outputs 0 or 1. So then the correctness is just half. Okay. With probability half, it can output the correct bit between 0 and 1. Okay. Plus there is another case that probability C2 minus M1 minus B mod P, this does not belong to G. If this element does not belong to G, then of course it can say with 100% probability that MB is the one which is encrypted in C1, C2. Okay, so that's why this probability is 1. And looking at this probability value, probability of C2 minus M1 minus P mod P belongs to G, as I said, is exactly half. Why? Because that P is of the form 2Q plus 1. So all the elements of ZP star, so they either, so with probability half, if you have n number of elements in ZP star, okay, so ZP star actually has P minus 1 number of elements, right? Now, half of them will belong to G, which is of cardinality Q, and half of them will not be in G. So this probability that some random element of ZP star belongs to G, that is half, and some random element in ZP star does not belong to G, that is also half. So this part becomes half into half, plus the second right side part becomes half into 1. So this is 1 by 4 plus half, which gives us 3 by 4, which is not negligible. So with non-negligible probability, the adversary is able to distinguish between encryption of M0 from encryption of M1. So we conclude that this scheme is not CPA secured. Okay. Proceeding to the next problem. So consider the following public key encryption scheme. The public key is GQ small g comma h and the private key is x generated as in L-Gamel encryption scheme, that is h is equal to g to the power x. Okay. So in order to encrypt a bit b, the sender does the following. If b equal to 0, choose a uniform y belonging to zq and compute c1 equal to g to the power y and c2 equal to h to the power y. The ciphertext is c1 comma c2. And if b is 1, then choose independent uniform y comma z belonging to zq. Compute c1 equal to g to the power y and c2 equal to g to the power z and set the ciphertext c1 comma c2. Show that it is possible to decrypt efficiently given knowledge of x. Proof that this encryption scheme is CPA secure if DDA's assumption is true with respect to G. This is interesting. In standard L-Gamel encryption scheme, your plaintext space is basically any group element of the group G. Okay, but here your plaintext space has been reduced to be just binary bit, like bit encryption scheme. Either B can be 0 or B can be 1. If B is 0, then your ciphertext has the form C1, C2, where C1 is z to the power y and C2 is h to the power y. And as you know, h is nothing but g to the power x. So C2 becomes g to the power xy. So overall, if you see the view of an adversary, okay, so adversary basically, whenever you talk about CPA security, the adversary has some chosen pair of plaintext, say M0, M1. Here the bits are only like both M0 and M1 are chosen from this space 0, 1. Okay. Now, so basically, if the adversary is seeing an encryption of 0, then H, C1, C2 is nothing but a valid Diffie-Hellman triplet visible to the adversary. Do you agree with me? So, I am saying that the public parameter h, as you know, is nothing but g to the power x, where x is private key. This is according to the standard L-Gamel encryption scheme. Right? Now, if you see together the triplet h, c1 and c2, h has of the form g to the power x, c1 is of the form g to the power y, and c2 is of the form h to the power y, which is equal to g to the power xy, because h is equal to g to the power x. So all over this is like g to the power x, g to the power y, g to the power xy, which is nothing but a valid Diffie-Hellman triplet visible to the adversary if the underlying plaintext is 0. And if the underlying plaintext is 1, then the ciphertext has the form C1, C2, where C1 is g to the power y and C2 is g to the power z for some uniformly random element yz belonging to zq. So all over, if you see that h, C1, C2 here has the form g to the power x, g to the power y, g to the power z. So this is uniform random triplet from the space capital G whole cube. Capital G is the group element space. G cube means that any 3 element chosen uniformly randomly, each from the group G. Okay. So this is nothing but the DDH problem. That the adversary, if it is able to solve the DDH problem in this setting, then it will be able to break the CPA security of this scheme here. But as we have already assumed here that DDH assumption is true with respect to G, then we say that Diffie-Hellman triplet is indistinguishable from uniformly random triplet the uh, of the space GQ. Okay. So we say that this encryption scheme is CPA secure. Okay, I just analyzed why the scheme is CPA secure. However, I forgot to mention that what is the decryption algorithm actually. So the question was show that it is possible to decrypt efficiently given knowledge of X. This is very trivial actually. Just see the form of the ciphertext. So if it is an encryption of B equal to 0, then it is always true that C2 is equal to C1 to the power X. X is the secret. So decryptor has the secret key X, right? So with the knowledge of secret key X, it can compute C1 to the power X and check whether that is equal to C2 or not. If that is satisfied, then it concludes that B equal to 0. So it concludes that the underlying plaintext bit is 0. And if it is not satisfied, that is C1 to the power X is not equal to C2, then it says that the underlying plaintext bit is 1. However, it may be the case that this value Z has been chosen in a way that Z is equal to XY. If that occurs, then actually, although the underlying bit is 1, C1 to the power X equal to C2 will be satisfied, and the decryptor will wrongly output the plaintext bit to be 0, although the actual plaintext bit is 1. But that will happen with very negligible probability, because if the value of Q is sufficiently large, then choosing some particular element XY from all the available Q elements of the set G, that is nothing but 1 by Q, which is negligible provided Q value of Q is very large. So with very small probability, there is some decryption error, but efficient decryption is possible with significantly high success probability. And I already discussed about the CPA security of this scheme, assuming that DDH problem is hard to solve with respect to G. So that is what it is written here also. Okay. So let me proceed to the next problem. Does Ilgamal encryption scheme provide CCA security? Explain. So as you may have already noted in the lectures also, that they have discussed about CPA security of Ilgamal encryption scheme, but it is not CCA secure. Okay? But you have to here describe formally that how an adversary. So you already know the definition of CCA security with respect to symmetric key and with respect to public key encryption as well. So in both the cases, basically the adversary is given access to the decryption oracle. So adversary can choose any ciphertext of its choice, and then it can see the corresponding plaintext of those chosen ciphertext. So chosen ciphertext, so adversary is given the access to the decryption oracle in this case. And if you are being said that you have to show Ilgamal encryption does not provide CCA security, then you have to find a way with which, by exploiting the free access to decryption oracle, you are able to say whether the challenge ciphertext is an encryption of M0 or it is an encryption of M0. So let's see the answer. So Ilgamal encryption scheme is not CCA secure. That is probably known to you also. So let us provide counter example to say that how CCA security can be broken. Let C1, C2 be the challenge ciphertext, which is encryption of either M0 or M1. Now, according to Ilgamal encryption, C1 is equal to G to the power Y for some uniformly chosen group element Y, right? And C2 is of the form H to the power Y into MB. Here, H is equal to G to the power X is the public parameter corresponding to secret group element X. That is also okay. Now the adversary simply computes C2 dash equal to C2 into H. So if the adversary is able to see the challenge ciphertext C1, C2. Now it computes C2 dash of the form C2 dot H. And C2 has the form H to the power Y dot MB. So H to the power Y remains as it is, and you just multiply the part H with MB. So I am placing the bracket in this way to denote that H to the power Y part remains as it is, but the underlying message changes to MB into H instead of MB. Okay. And now if you access the decryption oracle with this query ciphertext C1, C2 dash, C1 has the form G to the power Y and C2 dash has the form H to the power Y into MB into H. So this will give you the underlying message after decryption. So decryption oracle will return the value MB into H to the adversary. And as H was chosen by the adversary itself, so it can obviously compute H inverse on its own with respect to the group G. So with the knowledge of MBH and then computing the value H inverse, it can easily retrieve MB as MBH into H inverse. Okay, so H dot H inverse is nothing but the identity element, and MB into identity element gives the identity element itself. So you get back MB with probability 1 in fact. Okay. So this is how you can easily find out what is the underlying plain text MB given some challenge ciphertext C1, C2. So this is how CCA, we can say that Elgamal encryption scheme is not CCA secure. Proceeding to the next question. Say 3 users have RSA public keys in1, 3, in2, 3, in3, 3. That is, they all use public exponent or encryption exponent E equal to 3 with n1 less than n2 less than n3. Consider the following method for sending the message M belonging to a length binary string to each of these parties. So we first choose uniform R belonging to Z1, Zn1 star and send to everyone the following ciphertext: R cube mod n1, R cube mod n2, R cube mod n3, then HR XOR with M. This actually end bracket is missing here. There will be one bracket here. Okay, this bracket starts here. The bracket end is missing by mistake. So there will be another bracket here. Okay. So there are 4 components in the ciphertext, as you can see. Okay, and here H is said to be some, you can think of it as like some expanding function like PRG, but the seed is not of some specific length here, so it can be of any arbitrary length. Okay, so you can think it to be key derivation function, sum hash function. Okay, so it takes some random binary string and outputs some fixed length binary string which is uniformly random over the output space. Okay, so anyway, this you can think of some key derivation function. Now the and L is much greater than N. Now question is that show that the scheme is not CPA secure and adversary can recover M even if H is modeled as random. Okay. So even if H is a hash function modeled as random oracle, then also saying that this particular form of ciphertext does not ensure CPA security. Why? So if you remember from the lecture also, there it was discussed nicely that how using the same small value of E, okay, in spite of taking different modulus value n1, n2, n3, which even may be co-prime to each other, because if they are not co-prime to each other, then by default you can find the factorization of n1 or n2 or n3. So let's say if you have some common factor n2 and n3. So n2 and n3, if they are not co-prime, that means they have some common factor. And if it is there, then it is easily can be found out by performing GCD between n2 and n3. And once you have recovered one prime factorization of n2, then another factor is also easily recovered. So this corresponding P2 and Q2 corresponding to n2 and P3 and Q3 corresponding to n3 are easily recovered. Of course, some Pi will be equal to Qi because they are not co-prime. Now, with that scenario, actually, you can easily then once you have the factorization of both n2 and n3, you have the value of phi n2 and phi n3 as well. And then with the knowledge of E, you can compute the value of D in both the cases with respect to either phi n2 or phi n3, and you have the access to the decryption oracle, right? So you can compute E inverse for both the cases. So you have corresponding value, secret value D2 and D3, and with the knowledge of secret key, you can easily get the underlying plaintext value. Okay. So that is one case if these Ni and Nj are not co-prime to each other. But even if they are co-prime to each other, then also what happens is that you are keeping the value of E equal to 3 same for all these cases, and 3 is very small value. So computing cubic root for any given number modulo some integer in is easy. Okay. But so in this case, what happens is that if you say that let's denote this value as S1, S2, and S3, the first three component. So you have S1 is R cube modulo N1, S2 is R cube modulo N2, and S3 is R cube modulo N3. Then using the Chinese remainder theorem, where these modulus values have to be co-prime to each other, then you can get solution of the value R cube, okay, by solving the linear congruences simultaneously using the Chinese remainder theorem. And once you have value R cube modulo N1, N2, N3, basically whatever you get by solving Chinese remainder theorem over these three linear congruences, that value is congruent to R cube modulo N1 into N2 into N3. And once that is recovered, then you can easily recover the value of R. And with the knowledge of R, actually, you can compute H of R, and then you just XOR the value of H of R with the fourth component to recover the exact underlying plaintext M. So that is how it is saying that the scheme is not CPA secure, rather the scheme reveals the underlying plaintext M, right? So first part is done. Then the second part says that propose a simple fix to this and get a CPA secure encryption scheme where ciphertext size is 3L plus order of n. So just note that H of this H function maps the output to L length binary string. So fourth component has the length L, and the this modulo n kind of components, they have order of n, like so. Okay, you can think of this like binary representation of each of those ni's are upper bounded by some uh, polynomial function of n. Okay, so now so our main problem here in the encryption scheme proposed, the main problem was that they were choosing same value r for each of the cases, right? So the immediate alternate solution can be that if the encryptor chooses R1, R2, R3 separately for the three separate parties. So R1 belongs to Z1 star. If you just see that here R1 was chosen from in the question, R1 was chosen from Z1 star, while N1 was list of them, N1 less than N2 less than N3. So N1 is the smallest value. So any uniform R which belongs to Z N1 star will of course belong to Z N2 star and Z N3 star as well. Okay. Now here they are saying that R1 will be chosen from Z1, Zn1 star, R2 from Zn2 star, and R3 from Zn3 star for each of the three users. And then the ciphertext that needs to be sent to all of them is of the form R1 cube mod N1, R2 cube mod N2, R3 cube mod N3. Okay. And then H of R1 XORed with M, H of R2 XORed with M, H of R3 XORed with M. So after seeing such kind of ciphertext, each of the user, what they will do is that they will just see the value of Ri cube mod Ni and H of Ri XORed with M. And while decrypting, it will have the access to the value of corresponding Di. Okay. And then with the value of Di, basically it will compute Ri to the power ed, where is 3 here. So Ri to the power ed mod Ni, which will give R mod Ni, like Ri mod Ni. So corresponding Ri will be recovered by each of the corresponding parties. And with the value of Ri recovered by them, they will compute H of Ri and then they will recover the message value. Okay. So as the same R is not there, Chinese remainder theorem cannot be applied in this case, as you see. So yes, this is a valid modified encryption scheme where the previous attack is not applicable. Now, the third part of the question was, and also check the ciphertext size. So as there are three L-length binary string as the three components, last of the three components. Here, all of them have length L because hash function maps the output to L-length binary string. So this gives us 3L, and N being much less than L, all of these three, we can just represent them as order of N. So the size is actually 3L plus order of N in the second case. And the third question is that find a better CPA secure approach to get ciphertext size L plus order of N. So according to size, we are trying to get even more efficient approach. What we can do is that we will be choosing uniform random Ri from Zn9 star as before, but we will also choose another uniformly random K from n-bit binary string and construct the ciphertext as R1 cube mod N1, R2 cube mod N2, R3 cube mod N3. These are as previous. Then instead of XORing M to each of these H of Ri value, we will XOR K. So we get H of R1 XOR K, H of R2 XOR K, H of R3 XOR K, and then another additional component of the form ENC of M with respect to key K. And this ENC is some encryption algorithm of some secure symmetric key encryption scheme. And this key K is basically that symmetric key, some uniformly randomly chosen key from the key space of that symmetric key encryption scheme, and this key K will be first recovered by each of these uh, our parties. Okay, so each of them will basically recover Ri first, and they will recover the value of K first, and they will just run the corresponding decryption algorithm of the symmetric key crypto system with respect to key K and recover back the plain text M. Okay. So next question. Fix RSA public key n comma e and assume an algorithm A that always computes LSB of x given x to the power e mod n. Propose an algorithm A dash that computes x from x to the power e mod n. Okay. So this is interesting. Like, you are given the value of x to the power e mod n, and you are provided with some algorithm A which is able to derive the least significant bit of x. Now, if you are able to derive least significant bit of x, what you can immediately do to get the second least significant bit of x is that you just shift x, bitwise right shift the value x to get the value of x2, right? So you are actually having the value of x to the power e mod n. So if you are somehow able to manage the value of x by 2 to the power e mod n, then you are actually shifting one bit to the right. And now what if you run the algorithm A on that value x by 2 to the power e mod n, you will actually get the second least significant bit of the string x, right? So as simple as that. So that is what we will be doing step by step. So by applying A once, we can recover LSB of x. Now by applying the same algorithm on x by 2 to the power e mod n, we can recover second last bit of x. Okay. Then next time again you will run x by 4 to the power e. Basically, again right shifting one more bit, right? So like that, we will be able to recover one after another all the bits of x. And now our just one challenge is how to compute 1 by 2 to the power e mod n. So that is nothing but you can think that c equal to 2 inverse. Okay, 1 by 2 you can also write as 2 inverse mod n. If we denote that value c, so computing c, that is 2 inverse mod n, and then c to the power e mod n is easy modular inverse and modular exponentiation operation with the knowledge of both n and e. So we can compute x by updating x equal to x by 2 to the power e. So which is nothing but x to the power e value is available to you, x to the power e mod n. You are multiplying that with c to the power e. That is 1 by 2 to the power e. So you update at each iteration of the loop x to the power e to the power e mod n, and then like that in each step you recover the bits one after another by repeated application of it. Okay. So proceed to the next problem. Which of the following is or are true about security of RSA crypto system? This is very basic question actually. So I will pause if you would like to answer. First statement is RSA crypto system is COA secure provided RSA assumption holds true. Then it says RSA crypto system is not COA secure. RSA crypto system is not CPA secure and RSA crypto system is not CCA secure. If you would like to answer in chat or if you would like to unmute yourself, just answer. Okay. So basically, RSA crypto system is not CPA secure. Okay. I think, okay, so there is a mistake. Okay. RSA crypto system, as you know, so let us just recall. Okay. What is RSA crypto system? You have some large, you choose two large prime P and Q, right? Then you compute capital N equal to P into Q, and you also compute phi n, that is Euler-Taussig function of the value n as P minus 1 into Q minus 1. Okay, that is the value of phi n. Now you choose some E which is greater than 1 and which is also co-prime to the value of phi n, right? Yes. Yes, you can unmute yourself. You want to say something, Asia? Hello? I think you raised your hand. Okay. Okay. So, okay. You basically choose E greater than 1. GCD of E comma phi n is 1. That is, E should be co-prime to phi n. Okay. And then you compute D, which is nothing but E inverse of modulo phi n. And you output n comma E as the public key and n comma D as the secret key of your RSA crypto system, right? Now, whenever you have some message, plain text message X, okay, you compute its corresponding ciphertext as X to the power E modulo N, okay? Now, in case of RSA crypto system, the encryption algorithm is deterministic actually, okay? So, by seeing the value of X to the power E mod N, you actually cannot say what is the underlying value X, okay, because you don't know the secret key value D. While decrypting, if you are provided with some C, ciphertext C, which is nothing but X to the power E mod N, then you compute C to the power D, which is nothing but X to the power D E mod N, and that actually gives you back X to the power DE modulo phi n. So in the exponent, the value DE is congruent to DE mod phi n. Okay. And DE mod phi n value is 1. Okay. So that's how you get back C to the power D mod n equal to X mod n. That is the decryption algorithm. But without the knowledge of the secret value D, by seeing only X to the power E, you cannot comment about the value X. Okay. So that is what the RSA assumption says. Now, because RSA assumption holds true, that will only ensure that by seeing the ciphertext, you cannot actually say whether it is encrypting some x0 or x1. That is how we say that it is CoA secure. But what if you have the encryption oracle access? Then in the encryption query phase, you are not restricted to do any polynomial number of queries. So you can already query for the encryption value of x0 and see the value of x0 to the power e mod n. And you can also query the encryption oracle for the value x1 and see the value of x1 to the power e mod n. And because the encryption algorithm is deterministic, when you choose the challenge plain text to be m0, m1, and you get to see the corresponding ciphertext CB, which is mb to the power e mod n, that value is already, you can compare with the previous encryption query output values. Okay. Because the encryption algorithm is deterministic, you can easily distinguish between encryption of m0 and encryption of m1. So it is not CPA secure. Okay. And if it is not CPA secure, then of course it is not CCA secure. Some of the vulnerabilities of RSA crypto system arise due to the following scenarios. The encryption is randomized. One sends same message X to several users in a system using their respective key, where the encryption exponent E is small and same in all these public keys. Third statement says all the users have same public modulus N, but different encryption component E. Fourth statement says that encryption is performed using small encryption component E on short message, and then all of the above. Okay. So basically some of the vulnerabilities of RSA crypto system they are talking about. So first option, they are saying that encryption is randomized. This is of course wrong because basic RSA crypto system is deterministic, and that is the vulnerability of RSA crypto system, that it is not CPA secure. Okay. So first option is incorrect. Then one sends same message X to several users in a system using respective key, where the encryption exponent E is small and same in all these public. So just now we had seen one example where we were sending R to the power cube. So R cube mod n1, R cube mod n2, and R cube mod n3 to three different parties, right? So although the modulus n1, n2, and n3 are different for all these parties, the encryption exponent E is equal to 3 for all of them. And by seeing the corresponding ciphertext value, say C1, so C1 is equal to R cube mod n1, C2 is equal to R cube mod n2, and C3 is equal to R cube mod n3. By solving these three linear congruences using Chinese remainder theorem, will return you with the value x modulo n1 into n2 into n3, which satisfies the value, like you will have x which is congruent to R cube modulo n1 into n2 into n3, and you can definitely get back by calculating cube root of this value x to get the value underlying R. Okay. So this is one vulnerability of RS crypto system, where very small value of E like E equal to 3 is chosen, and for E equal to 3 is chosen for all the users in a system. So that is one vulnerability. And then another option says all the users have same public modulus N, but different encryption component E. So if you have seen in the lecture, there is also another nice attack on RS crypto system when the encryption modulo E are different. So U1, E2, E3 are different, but same N is used in all these cases. Okay. Then also x to the power E1 mod n, x to the power E2 mod n, and x to the power E3 mod n, these values will be visible, and you can easily compute the value of like you can come up with the corresponding secret key values, and your RSA crypto system is vulnerable to such attack. So these details are discussed in your the videos posted in the NPTEL website. And the next option is encryption is performed using small encryption component E on short message. So in this case also, if you choose very small E and then the message you are encrypting with that is also within some range, very short range, then what happens is that even if you compute x to the power E mod n, that value of x to the power E basically actually is less than n. So the effect of doing modulus operation with modular value n has no effect. X to the power E is itself actually the value which is less than n. So you can directly compute eth root of x from that, eth root of x to the power E, and get back x, right? So this is also another vulnerability of RSA crypto system. So basically, except the first option, all the second, third, and fourth statements are actually vulnerability of RSA crypto system. Third option is not included here. This is also another vulnerability. Okay, so this will also be included in the answer. Next question, which of the following statements is or are true? The padded RSA crypto system provides CPA security while the basic RSA does not. Yes, that is true. Because basic RSA does not provide CPA security, that's why we proceed to encrypting some shorter length of messages by providing some particular length of random bits padded to it, and we try to ensure that the encryption algorithm is randomized by the random choice of these padded bits, and then as the encryption algorithm now becomes randomized, we look forward to achieve CPA security. So yes, first option is correct. Second option, Elgamal encryption provides CPA security. So this is true. We already discussed in previous question that Elgamal encryption provides CPA security because it has the internal randomness. Whenever an encryptor or a sender encrypts some new message M, it chooses some random value Y from the set ZQ, where Q is the size of the cyclic group G. Okay, it chooses some uniformly random Y and provides the ciphertext as C1, C2, where C1 has the form G to the power Y and C2 has the form of M into H to the power Y, right? Where H is G to the power X available as public key, right? Now, because this value of Y is random, each time it encrypts the value M, so it is randomized encryption algorithm, and Elgamal encryption satisfies CPA security. Okay, but it does not satisfy CCA security that we already discussed in a previous question. Now, third statement says the length of padding in padded RSA, if smaller, may lead to brute force attack to recover plain text. Yes, this is true because the padded length, the length of padding L is known. Okay, now any adversary can basically exhaustively search through the space 0 to the power 0 to 2 to the power L minus 1 for all the possible value of this randomness which is padded to the original message M, and by observing that which of the M cap, where M cap is the padded version of the underlying message M, which of the M cap actually gives us back the ciphertext that we are seeing. So by doing such exhaustive randomness space search, we can attack the RSA crypto system. And this is possible if L is too small to perform such exhaustive search attack. Okay, so L should be sufficiently large to just ensure that such attack does not occur. And the next option is the length of padding in padded RSA, if larger, may lead to inefficient communication as communicated messages shorter length. This is also true because you have certain size of the plain text. Let's say some 1024 bits of messages supported by original RSA crypto system, let's say. Then if you were allocating the length of L, that is the number of padded bits, if you were keeping L to be much larger, then the actual message which is there in the message block, that will be very short. So padded length of bits are more larger than the actual message which is being communicated. So the communication becomes inefficient. So yes, the fourth statement is also true. So basically all the above statements are true here. So next question. Consider RSA parameters n, p, q and public key n, e, private key n, d. Now some statements are given. If plaintext is in Zn star, correctness of decryption relies on the fact that ed is congruent to 1 modulo phi n. Second option says if plaintext is in Zn, correctness of decryption relies on the fact that x to the power ed congruent to x modulo phi n. Third statement says RSA decryption with large private key D can be computed faster using the fact that if x belong to Zn star can be represented as y, z belonging to zp star cross zq star, then fx mod n can be represented as fy mod p, fz mod q. So basically, if we just go through one after another. So first option, this is the property of correctness of basic RSA crypto system, where we say that if plaintext is belonging to Zn star, then when you are given a ciphertext of the form x to the power e mod n, and then you try to decrypt it by computing x to the power e whole to the power d mod n, that is x to the power ed mod n. Okay. Now ed is
the answer is all of them.
Hello, yes. Acha, okay.
The answer is all of them.
Yes, the answer is all of them. Thank you. Yes. So the first option is very trivial to the basic RSA crypto system, and then the second option we actually saw in the padded RSA crypto system, where the after padding, whatever bit string we receive, it may not be member of Zn star, so it may be member of Zn only. Okay. But then also this condition is satisfied, the decryption correctness is satisfied, but that is due to the fact that x to the power ed is actually congruent to x modulo phi n, and that's why we could write x to the power ed mod n is equal to x mod n. Okay, so this should be actually n, okay, not phi n. That is a mistake. X to the power ed congruent to x mod n actually. Okay. And then RSA decryption with large private key D can be computed faster using this fact. So there was this bijection through Chinese remainder theorem, where you have any element x belonging to Zn star, and you can have one representation of this element by projecting it to different set of Zp star and Zq star of two different elements y, z. And if this is the representation corresponding to x, then this condition that applying any function fx mod n on the set Zn star will be equivalent to the representation of Fy mod P in this set Zp star and Fz mod Q in the set Zq star. So this property is used when we have very large decryption key D and our decryption operation is very computation heavy. Then we actually divide these operations in modulo P and modulo Q and get faster decryption process. Okay. So if you would like to answer this question, I'll just read out once. Consider pi KEM equal to J encaps decaps to be a key encapsulation mechanism. Select the correct statements. J is a randomized algorithm and outputs one public component PK and one private component SK. Both encapsulation and decapsulation are deterministic algorithms. Output of encapsulation consists of a key K and its corresponding encapsulation C, which is equal to encapsulation of K with respect to PK. And encapsulation C is kept secret and key K is communicated through public channel. If you would like to answer. Okay, so is first option, Jane is a randomized algorithm, which is true basically. So in key encapsulation mechanism, your Jane algorithm outputs two different key, PK and SK. PK is the public component and SK is the secret component. First statement is true. The second statement, both encapsulation and decapsulation are deterministic. This is wrong. Encapsulation algorithm is randomized and decapsulation algorithm is deterministic. Okay. And then encapsulation outputs a key K. So this key K is actually chosen uniformly randomly from some key space. And then encapsulation operation is performed on this key K using the public key PK. Okay, and you get the encapsulation of key K as C. So K and C both are output of the encapsulation algorithm, while C is the encapsulation of key K with respect to PK. Okay, and then while decapsulation, just to complete, so K comma C is the output of encapsulation algorithm, but only C is communicated on the other side. Okay, and the decapsulation is performed as you take C and you take as input the secret SK and you get back the corresponding key K. Okay. Now it says the fourth option says, so third option is correct. Fourth option says that encapsulation C is kept secret and key K is communicated through public channel. This is wrong because basically encapsulation C is communicated because it hides the key K inside it. So C is actually communicated, not the key K. K is kept secret. So first option is correct and third option is correct. Next question, select the correct statements. Combining a COA secure KEM and COA secure symmetric key encryption scheme leads to a COA secure public key encryption scheme. Second option says combining COA secure KEM and a COA secure symmetric key encryption scheme leads to a CPA secure public key encryption scheme. Third option says in a hybrid encryption scheme constructed by composing COA secure encryption scheme with COA secure KEM generates ciphertext of the form C1, C2, where C1 is an encapsulation of encapsulation of the symmetric key used in encryption under public key PK, and C2 is an encryption of some plaintext M under symmetric key K. So, okay, you would like to answer? Okay, so basically all of them are correct. So this is clearly discussed actually in the lectures also, that if you have two components, one is COA secure key encapsulation mechanism and one COA secure symmetric key encryption scheme, then you compose them together in a way that is actually described in this third statement, that how do you construct this composition. So basically your COA secure KEM first outputs some key K, which is going to be used as symmetric key for encryption. So key K is chosen randomly and its corresponding encapsulation C1 is generated with respect to public key PK. Okay. And now this key K is used to encrypt the message M with symmetric encryption scheme, and the corresponding output is C2. And C1, C2 is together the corresponding ciphertext. Okay. And during decryption, what happens is that the decryptor first takes the first component of ciphertext C1 and pass it through the decapsulation algorithm with respect to the secret key SK, and it gets the key K, and then using the symmetric key K, it applies decryption algorithm on the ciphertext component C2 and gets the corresponding message M recovered. So that is how you compose these two secure construction. And if your component KEM and component symmetric key encryption scheme both are COA secure, then your generated hybrid encryption scheme is CPA secure. And if it is CPA secure, then of course it is COA secure also. So all the three statements are correct. And just to mention that if the component KEM and component symmetric key encryption scheme would have been CCA secure, then the resulting hybrid encryption scheme also would be CCA secure. Okay. So that's all for today. If you have any question, then ask, and otherwise I can end the meeting. Okay. Bye then.